I've been asked to kind of give a bit of my history because the research you guys do, I don't do, and the research I do, you don't do, so what are we going to talk about? So it's going to be more of a little path and history thing. So you should learn a little bit about your chair. In case you need the diagrams, there's the visualization thing. But there might be actually some points to this a little bit later. That's the corny joke, Bill. We're good? Okay. All right. Started off at Williams Hill College. Going to be an atomic physicist. This is 1979, 1980. Nuclear physics, atomic physics, that was cool stuff. Slam those things into each other, see what happens. That's what I was going to be. Okay. So the first thing that went wrong was in the early 80s, they were going to build this big Texas super collider over in that town, Texas. Anybody can say that? I can't. Okay. And so this is going to be a bigly funded thing, and we're going to have lots of atomic physicists and nuclear physicists and jobs galore. And what they do with that? They axed it. So all those fantastic physicists were out of jobs. I'm going to compete with them, but that's only the first problem. The second problem was the Berlin Wall came down, and all of these Russian physicists were coming over here saying, $25,000 a year, I could have my own apartment. This is great. And so all of a sudden there's this big glut of fantastic, highly educated, highly talented physicists, and I'm going to compete with that. So guess what happens when that occurs? Time to change careers, right? So out goes the atomic physics. Ended up at the University of Alabama in Huntsville. Anybody ever been to Huntsville?
Mm-hmm.
What's in Huntsville?
Well, it's now MDA, but not by then.
Oh, bigger than that.
Rocket science.
NASA. Okay, that's where Wernher von Braun lived, right? NASA started in Huntsville. It wasn't called NASA back then. It was, I can't remember, before my time, okay? And because of that, the university there was, you've heard of land grant institutions? Okay, the government gives land to the university, whatever. This was a space grant institution. I'm not kidding. That's an official designation, okay? And because Marshall Space Flight Center was there, a lot of the experiments in the university and research was tied to flights in space. Cool. Forget about atomic physics. I'm fine with that. I'm going to do space stuff, right? And so I got hooked up in a group that was doing crystal growth because what they wanted was a material that had a gradient index of refraction, which means it would look like a curved mirror if it was flat, because the index of refraction would change. They wanted the opposite thing. They wanted a curved piece of glass that looked like a flat piece of glass, because the curved piece of glass was on the front of a missile or a rocket or some things we're not going to talk about. And it had to be open to the and so zinc index infrared material. And the idea was this material could have zero resistance to a flow of electricity at a temperature above 92 Kelvin. The reason that's important is the first cheap coolant is liquid nitrogen at about 88 Kelvin. Anything less than that, it's very expensive. So all of a sudden, they could do cheap superconductivity experiments. And for a couple of years, this was fantastic research. Lots of money pouring into it. The colonels and the generals are all excited about it. CNN was excited about it. You can now buy the material on Edmunds Scientific, and that's about as far as it went. It worked, but it was too brittle to do anything with. So the attention was going away from the crystal growth, going to anyplace else, so we could grow the crystals on the end of this tip. Seemed like a good idea at the time. It was really kind of neat. I mean, like I said, this is 1,000 Celsius. You could actually touch this pipe on the sides, not for very long, but you could touch it. But you put anything on this end, it would burn you in a second. So it's piping all that heat out of there. All right, cool. What does it have to do with computational data science? Well, the project we did was, what should be the shape of this angle here? Okay, we wanted to maximize the coolant. Is that the best shape, or is some certain angle the best shape, or is the conical thing the best shape? So we had to build programs to do a lot of simulations and of this system and try to find out what was the best coolant and make sure that it was the same temperature across the face. There was actually an angle, flat angle, that worked better. Okay, so simulations. It fits in this group somehow. All right. But like I said, the shuttle blew up, so we had to go do something else. And in Huntsville is also the Center for Optical Sciences at the University of Alabama in Huntsville. It was run by Dr. John Caulfield at the time, who was one of the gurus of holography. And at the time, computers were really slow. We're talking about 286s. You know what that means? Okay, only half of you are smiling, the ones with gray hairs. This is an old computer. In fact, it was so old it couldn't do floating point math well. You had to pay an extra $1,000 to get a floating point processor stuck onto it, okay? And it had a whopping 640K of memory. K.
Should be enough for anyone.
What?
Should be enough for anyone.
Yeah, we're good. That's right. What the hell you need a meg for, right? 10 megabyte hard drive. Okay, so computers are really, really slow. They didn't do a lot of stuff. So a couple of things that were going on. One was, can we build transistors out of optical materials rather than electronic materials? And the electronic things only had 2 levels of logic, 0 and 1. We could do 10 levels of logic. Therefore, we're better. Turns out that's not true. The logic thing, not the better thing. 10 levels of logic is the same as 10 transistors of binary logic. Whoop-de-doo. There was no big gain in there. But they were also working on how do you integrate the optics? You want to put it on a little chip, right? Instead of running electrons around, how do you deal with photons? Well, the nice thing about photons is they don't interact with each other. So I understand in electrons, there's a certain distance, so you can't put 2 wires any closer to that because they start talking to each other. And when you integrate optics, that's important. Photons don't care. They can go through each other. We can go back the other way. We don't care. But they don't turn corners. And so that was a lot of real estate. And getting photons started and getting photons stopped is very, very expensive. So it was a really neat idea that didn't really work that well. But there was a lot of simulations on how to do optical waveguides. The really frustrating thing was that photons, when you do this kind of thing, they have to be synchronized, coherent, in the same phase. And if they get out of phase, then the information starts spreading and your wave packet starts spreading and you lose your bandwidth. So no matter what you do to the photons, you have to make sure everybody's still in lockstep. That's why you can't fix fiber optics very well. In a wire, if it snaps, you just weld it back together, you're good to go. You can't do that with fiber optics because when you go through that messy junction, it changes the modes and you lose your bandwidth. All right, so we were working on transistors and optics waveguides, but I got involved in more of an image analysis kind of thing. So, do you know correlations, convolutions? Okay, so the idea is that you have this picture here which has a bunch of pixels, black and white and gray and all sorts of things. And we have a mask that in this case the mask is going to look just like it. And this is the picture. We want to know, is our target inside this picture? Of course you can say yes, because you know it is, but we may not know it. And there may be other things in the picture as well besides our target and stuff like that. And so in a correlation, what you do is you take you've got your input image, and then you're going to take your other image and you slide it by, and for every possible shift, relative shift, you do a dot product and see if the pixels line up. In one dimension, it looks something like this. So we're doing all this sliding, and for every possible slide, we sum things up, and when they line up, we get a big signal because you got a whole bunch of positive pixels lining up with a whole bunch of positive pixels. And then when you go further, it doesn't. So you would have, in this case, a signal that's kind of bumpy, and all of a sudden, spike, and then bumpy, bumpy, bumpy. And the presence of the spike says you've got a match. What was in your mask was in your picture. The location of the spike tells you where it was. So if it's shifted in the input image, if your target is shifted, the spike will be shifted. Now I only showed you 1D, we'd also do it in this direction too. Okay? Simple math. That was an easy way of doing some target recognition at the time. In the optics world, where I was living, it turns out that a positive lens, fat in the middle, thin on around the sides, will perform a Fourier transform. You don't believe me? You ever fry an ant? Yeah, you remember you're a kid, right? Yeah. Okay. What is happening is you've got these parallel light beams that are all being focused down on there, but it's actually doing a Fourier transform because you have parallel light beams. Now, to do this in a computational way, you needed a parallel light beams that were also monochromatic. So we use a laser, fatten it up, send it through a lens, and it would perform the Fourier transform. So if your light beam went through a mask that had an image on it, it would perform the Fourier transform of that image. Okay? It turns out that when you perform correlations in a computer, the fastest way to do it is to do it in Fourier space. You take the Fourier transform of your mask, you take the transform of your image, you just multiply them together, then you take the inverse transform, and you perform a correlation, and it's a gazillion because we can do fast Fourier transforms. Or we can do this in optics. So that sliding thing I just showed you, we could do it at the speed of light. And back then, 286s couldn't. Okay, again, efficiency in Fourier space. So we got into building these optical systems. This has got an input. You got 4 lenses here, so we're doing 4 correlations at the same time. This is the lens that did the Fourier transforms. So this is a mask that is matching the target to the input, and then some output devices here, depending on how you want to do it. That's not one I built, but they kind of look like that. What we wanted to do was what's called solid optics. This is one solid, because the thing on the table that I showed you with all those nice mounts, the picture, that didn't fly very well. Okay? And even if you could get the big table on the airplane without somebody complaining, it would torque. So you can't have free space between the optical elements because things won't line up. And in the optics world, you've got to stay aligned within 1/3 of the wavelength of light. That's small. Okay? So we wanted to build solid devices, one chunk of glass. Now it's got different types of glass in it. That would be the lenses. Instead of free space in here, we have a different type of glass. So you'd have an input, and it would go down here and hit this hologram, which would act as the filter, and then it would come back and hit a beam splitter and go off to the detector array. That sounds like fun, right? So this is the one we built at Teledyne Brown. It is 12 inches long. It's not all there because if it's all there, you can't see anything. This was the input side. If you can see these lines right here, these are where the lenses are, and there's another set of lenses here. And so the light would go into this device. It would go through what's called a spatial light modulator. It's a liquid crystal display. That's all it is. So you'd have a fat beam of light, and then this pattern is on the light. You would do the Fourier transforms. Here would be a hologram. It's not shown. It would bounce off of that, go back here, and take a right turn and go off to the detector. Speed of light, computations, fast Fourier transforms. I mean, correlations. Much faster than the computer, except you need a computer to feed the thing, and you need a computer to read out the thing. But we were on a contract number, so we didn't tell anybody about that because we liked getting paid. This worked. We were identifying tanks driving in video real time. So you had the tank driving down on the screen, and then we'd see the dot where we were, which means we identified it and we knew what it was. What was really cool about this hologram, not shown here, was we had to expose the film, and then go off and develop the film, and then put the film right back in the same exact position within 1/3 of the wavelength of light in a half a second. How do you do that? Okay, well, you can sit there and fiddle with mounts and stuff. So what we did, there was a flange, a metal flange, it's just a circular thing with a hole in it that fit on the end of here, and another one that looked just like it that the film was in. And we wanted to mate those two things. And the first one had 3 holes. Okay, and the second one had the same 3 holes, but in each hole was 2 bars. And in these holes, we'd put these round balls. So 2 bars would hit onto one of those balls at this location, and this location. We have 6 degrees of freedom, rotation, and you have 6 points of contact. It snapped right back into place. So it was cool. Mechanics, no computations. So we were doing that. 12 inches in length is too long, so then we went to the hockey puck design. This was cool. This thing was just about 3 inches by 3 inches, and we flew this on. Okay, so the light comes in here. It's a big fat beam. You've got a spatial light modulator here, which writes your pattern. This is a beam splitter, so at this point, the light will take a right turn. How does it know to take a right turn? It's a polarizing beam splitter. So all the light polarized this way, it'll hit that interface and take a right turn. If it's polarized this way, it goes straight through it. Okay. So it takes a right turn, bounces off this wall. This is one of the Fourier transform lenses. Bounces off this wall, goes up through the spatial, this thing, goes through our filter, bounces up here, goes through another lens, backing out. So folding it up, make it smaller. Cool, right? Same answer as the previous one, but much smaller. All right, computational science. Remember that, computational science. Where's the computational science going? You remember this, Rob. The ladies.
I don't know. Where's the beef?
Thank you. It's the old guy. Come on, people. Where's the beef? You don't know this?
Oh, where's the beef?
The commercial that saved Wendy's. Okay. The correlations I showed you was exactly the same pattern crawling across here, right? And it worked. But if I made one pattern just slightly smaller, it couldn't line up anymore. Okay? So the correlation idea worked really well if you had perfect data. Who has perfect data? Raise your hand. Okay, so we had to come up with something better than that. So we came up with these, this is called a fractional power filter. And the data is in X. So X columns in this matrix are the different input images that have been rastered. And then we have these other matrices, D, we'll talk about in a second, the C vector, which is a whole bunch of ones. And the idea was we're going to build this one filter that would react to several images in the same way. How it reacts is controlled by C. The images it reacts to are in these X's, and the D's is something that we have to compute with. D looks like this. It's a big, huge diagonal matrix. How many pixels you got? 1 million. This matrix is 1 million by 1 million, but we only deal with the diagonal elements. That's cool. And it has to deal with the energies of the inputs. And its D has always got a minus power to it. So things that have lots of energy before would be decreased in power in our filter. Things that have less energy would be increased. And when you deal with images, the things that have lots of energy are the interior parts of the object, and the things that have less energy are the edges. Well, edges define shape, so this thing became a little bit more shape sensitive. Well, that's good, because we're looking for shapes. Okay. And, well, I just told you, that's the inverse thing. My big contribution to this science was this alpha. I just want you to see the alpha because that was me, okay? All right. It was originally, the original theory didn't have the D's in here. Okay, cool. And then somebody came along and said, well, you can minimize the energy and get this nice edge-sensitive thing if you put a 2 there. I said, well, what if you go in between? Got lots of papers out of that. The other thing that was hurting us was that this light had to go through a spatial light modulator at times, a liquid crystal display. You know how those things work? Okay, so you got light coming through this, or you got a polarizing plate, so it's going to polarize light one way, and you got another polarizing plate here, okay? And if they're not pointing in the same direction, light doesn't go through. And you've got these liquid crystals in here, and if you activate them by turning on a voltage, they rotate the crystals, and it will rotate the polarization as the light goes through. So you can let light through, or you can turn the voltage off, and it doesn't let light through, or whichever way you design to do it. Okay. The problem is that photons are complex numbers. There's got an amplitude and a phase. Okay. So it's a complex number. The spatial light modulators are pass-through or not pass-through. That's not a complex number. How do you put complex numbers on a non-complex number kind of thing? Actually, the spatial light modulators, I lied to you. This is a complex graph, okay? And the numbers that the spatial light modulator could realize would follow along a curve like that. So it was living in complex space, but not everywhere, just on this line. So we had to do the computation to get our filters to fit all the values on this line without destroying the performance of the filter. Okay. It was a lot of fun. A lot of simulations again, a lot of computations. It made me go live in Houston for a little bit with a crazy man. He had a little Honda, and it had 2 modes. You push the pedal down all the way this way, or you push the other pedal down all the way, and that's how he drove. So it was a scary time. So it's one of those things like, get the work done quick, and let's go home. Once we got the correlations under foot, we went off to another school, and neural networks was a big thing. We're going to do computations in neural networks. And again, we're doing with 286s, 386s, and my God, the real expensive 486s were coming online. And the idea was that we can do optical computations and do these neural networks at the speed of light, because these things are basically just a bunch of multiplies and adds, and photons can do that. So again, there were designs in optical systems. By this time, I decided optics was not going to live. We had fiber optics, we had CD-ROMs, we had holographic memories, but everything else we were working on didn't look like it was going to survive. So we went back to studying what goes on inside of the neural network. When you build a neural network, what do? You got a bunch of inputs, that depends on your data. You got a bunch of outputs, that depends on your data. How many of these hidden neurons do you use? How many do you use? Try it, see what happens. Does it work? Nope, try another number, right? Okay, we didn't want to do that. We wanted to build a system that would determine the number of hidden neurons and determine exactly what their purposes were, so that you could go back and look at how the connections were in and out of the hidden neurons, and that would tell you something about what's going on in your data. And it worked really well for clean data, not so well for dirty data. So it was an academic exercise. In 1993, some German scientists were tearing apart the brains of cats for fun, analyzing the visual cortex and how those neurons work, and they came up with a model of the visual cortex neurons, which were not simple multiply adds. They were much more complicated. It had several compartments, where you would receive inputs at one thing, and it would add things up, and some inputs from other things, and they would combine in a second order fashion and compared to a threshold that was dynamic. So it kept changing too, depending on what the activity was in the output. So if the thing fired, it would actually change the threshold, and then the threshold would change in time. Okay, much more complicated neuron. And they were doing it because they were messing around with the brain of the cat. And at the same time, some Russians were doing the same thing to macaques, I think it was. And came up with a very similar design. And we decided, this was at University of Alabama, or Alabama A&M University in Huntsville, and Marshall Space Flight Center. And we built simulations of this thing and then started applying it to image analysis. And from these things, we could segment images. Foveation is to track your eyes, move your eye to the important part of the image. Texture recognition, is it smooth, is it flat, is it bumpy, does it look like bricks, does it look like fabric, that kind of thing. Can we identify objects in the picture? Logic, the spaghetti problem. Okay, so if I give you a whole bunch of strands of spaghetti and they're all different lengths, and I say, what's the tallest one, what do? You measure each one? No, you grab them all, you go, the tallest one's there, right? And it's a parallel computation. So we were doing the same thing with logic, because these neurons were all connected to each other, and the logic would flow in what's called autowaves. And then we went after big problems like traveling salesmen. Okay, and from that, I accidentally wrote a book. Accidentally. I was moving to George Mason. This is back when we had disks, little floppy disks, and I didn't want information to get lost, so I put it all together on these floppy disks, and my partner at the time said, I'm writing this book on wavelets. This is cool. And I said, well, I got some stuff. Throw it in the back, you know. We worked on it together. Come on. About 3 months later, he said, well, I sold your book. You did what? What book? And he sold it to this company that was a no-name company, and then they got Springer bought him out, so it was an accidental book. But it was success. We went through 3 editions, and then that edition, which was really fun because they sent me the galleys and said, proofread this. Pictures look good. It's okay, it's good, send it off. I wrote a book I can't read. Okay, so here's what so you'd have an input image like this. This is for my ASIP students. You know the ASIP program? Aspiring Scientist Summer Internship Program. It's run out of the Prince William campus, but it's on the Fairfax campus. And during the summer, they provide students who are either seniors in high schools or junior in colleges to work in your labs for free for a couple of months. Okay? It's run by Amy Van Meter out of the Prince William campus. Half of the students are from TJ. You have to tell them to go home. It's 5 o'clock, guys, leave, and they won't do it. But there's my TJ students who are working hard at the Prince William campus. But I took this picture, and what the pulse-coupled network, which is all these different types of neurons from the cat, are doing, well, it will activate neurons at certain times. So this is time 1, time 5, time 6, I don't remember exactly what they were. But we can see things lighting up in synchronous behavior. So like the sidewalk all lights up at the same time. You want to look for the sidewalk? You look in this picture. And finding the sidewalk in this picture is a lot easier than finding a sidewalk in this picture. Okay? So the neurons were all cycled. They'll all eventually fire over a certain amount of time, and then they're going to fire again because that threshold keeps changing. But the second time around, you see a different pattern. So here you got this broad thing here and here, but now the sidewalk's not lighting up at this time. And what is happening is the neurons are desynchronizing according to the texture that's in the picture. So we can go after shapes, objects, and texture by analyzing these binary images, which is easier than analyzing the original color image. Okay? And I got a lot of work out of my students. Okay. Actually, this type of equation you've probably seen. It may be on the walls, I know, because what it is a bunch of coupled differential equations. And the whole world works off of coupled differential equations, including, snarfed from Google, this material, that's the model, but the material was this protein that they would get out of the swamps of Mississippi and use it to an optical material. And you'd hit it with light, and it would start behaving like this, but it wasn't very fast. It was really cool, but it wasn't fast enough in the computations. And we were messing around with that. I can't remember the name material. But this kind of computations, every little pixel is a node, and every little node has a couple of differential equations attached to it deciding its state, and it's all talking to its local neighbors, not the global neighbors. And we see that everywhere. Okay, so the brain model was something we could use for lots of different things now. WATOR, do you remember this? This is one of the very first simulations, and you probably remember this, right? Fish and sharks. Okay, look it up, and Google has it, okay? It's one of the first simulations that we had about interacting things in a small grid. The fish multiply, and the sharks multiply slower, but the sharks eat the fish. And, okay.
Remember Watt 4? Watt 4 was Waterloo Fortran.
Yeah, it was probably the Fortran version of that. You're probably right in the same neighborhood, okay? Well, it's like the 1970s all over again. Moved here in 1997 to start the Institute. I was one of the first original members of the Institute for Biosciences, Bioinformatics, and Biotechnology, IB3. Funding for 10 years, lasted 10 months. Okay? But this is what got us here at this was the anchor group over there at Prince William campus. And we were going to do all this bioinformatics research. It turned out we ended up doing bioinformatics education because that's where the money is, but we did have the first PhD in bioinformatics on the whole planet. Now, other planets I'm not so sure of, but on this planet we were first. Okay? And for a while there was the only place to go, and so we were getting lots of quality students from the Beltway. And then when Johns Hopkins opened up a satellite campus over by where all the bioinformatics students work, right across the street, then the program took a dive. Okay, but there was a lot of image analysis to go on to that because there's biological images, microscopic images of cells, things like that. There's our different ways of presenting DNA as images rather than as a string of letters. And then we started teaching class in programming skills and got another accidental book, okay, which is now 10 years old. All right, started teaching in the forensics department. And the first class I had was, our teacher quit, left, go. Can you take over this class? I know nothing of this stuff. Don't worry, we have guest lectures for all the classes. All you have to do is sit there and write the final and learn. Okay, cool. And I'm sitting there going, well, this is kind of easy stuff, man. We can make a little program to simulate what's going on in the forensic DNA world. Cool, why not? So let's write a little program. And you know how it goes, right? Okay, thousands and thousands of lines of Python code later. What we ended up with was this simulation that was kind of cool. And it's kind of an educational game. So we have this theoretical island, and it has populations on it, a whole bunch of people. We have 4 different ethnic groups because ethnicity changes how we analyze the DNA. The statistics are different. And we had 5 different cities, 4 of which were highly concentrated with one ethnic group or the other, and then one which was a metropolitan area, which affects the statistics again. There was also a migration. The original group, the Pugs, came in at one part of the island and migrated, and every time they moved, they left people behind, and so we could do mitochondrial DNA analysis and backtrack the migration. But what the students really did was we'd give them a crime or a plane crash or something, and so the plane goes down. You got 20 people on board. We know the names of the people. We got the bodies with the DNA. Match the names of the bodies. How do you do it? Well, you have to go find the relatives and find out what their DNA profiles are and match their DNA profiles with the people on the board. Of course, if you have mitochondrial DNA or Y STR data, you can match people in the same family, because all the guys in the family have the same Y stuff, except for mutations. And everybody has the same mito as mom. So if you have 5 people with the same mito, they're from the same family, so you can group people that way. And then you go off and ask relatives to donate their DNA profile, and you can try to match that profile with the people on board, and you can identify the bodies. Or we'd have murder things, or we'd have a mixture, so you'd have an attack where the blood from 2 people mixed together, and you got to sort the DNA out of that. We had to have sex crimes because the DNA is treated differently on those. And they would interface to this website and ask for information about people. That would give them relatives, birth and records, marriage and divorces, immigration. And of course, in most countries, if you go to jail, your DNA is on profile. So if you're in jail, you have more information available than people running around the public. So our jailbirds were different than the other people. And the students would have to gather some samples, create the statistical analysis charts, and then we give them the crime. They had to use their data to figure out who did what, where, and stuff like that. We did it in graduate school, but we also did it down into the middle school. And for the middle schoolers, we gave them a plane crash with 20 people on board, 2 families, the rest were scattered, teams of 2, 8th graders, and they did it in an hour. They had a blast. They were better than the graduate students. The idea was that DNA is cool, let's add faces and fingerprints and lots of other forensic analysis kind of stuff, but then I didn't teach in forensics anymore, so we don't do this anymore. But this is still running on a server somewhere. The computational science as well, this simulation turned out to be very big. Right now there's, well, not huge by your standards, right now there's 150,000 different people in it running around on this island. Every night at 3 a.m. they advance 1 month, time passes. They, if you have kids, you got to inherit the DNA, right? So you got to work with that. They have to get married to have the kids, and then they have to get divorces and then get remarried. Okay, they move around. Some groups move more than others. They die. Dang them. They have to have personalities because some families commit murder and some families rob banks, and most families don't. And so there's things that have to be inherited besides the DNA. We had to have 4 different ethnic groups because the statistics are different. And you have to have things like cheating. Yeah. What happened was the FBI, when they started doing DNA analysis for like missing persons, they'd have the victims there, and they had the DNA from the body that they found, and they want to go check to see if it belongs to mom and dad, so they take the DNA from mom and dad, and they were finding out that in more than 8% of the cases, that wasn't dad. They said it became a real problem because we're not here to break up the marriage, so they made the policy of only checking with mom first, because that was actually a rampant problem. So we had to throw it in there. And if you have adoptions, you don't have any records, they're sealed. And then we'd have airplane crashes, all sorts of neat things. So at night, when you have watched your TV shows and you brush your teeth and you're laying in bed and say, okay, I got to come up with a murder for tomorrow. It's a fun job. I don't do that anymore. So once we got involved in some teaching over here, have you all been to the active learning room? This is over in bottom of Exploratory Hall right next to the bus stop. And this is a cool room that has these 8 round tables, seats of 9s. We worked in groups of 3, so 3 groups of 3 at each table, 72 students. And the room was designed that there's no lecture. It's flipped. You watch the videos before you come to class, you do the work when you get into the classroom, okay? And the walls, unlike this wall, you can write on them all day long, all the way around. It's really cool. So the students don't sit there, they get up. And they work in groups, they solve problems, they do what we need to do. Every table's got a TV. It's a really cool room. Okay. Amin Jaziri was supposed to teach the physics class in that in August, and the June before that, or the July before that, he said, I'm leaving. And they said, Jason, you're it. So I didn't have the year to plan for this, I had 2 months. And it turned out to be a really good idea because everything we thought we were going to do was wrong, and so we did it on the fly anyway. What was really cool, this was for Physics 160, so we had a lecture class that had 200 students, and then my class had 72 students. And they were running at the same time of day, so we could run exactly the same exams at the same time and then compare the grades. And so one of them is the lecture class, the blue line, and this one is the alt class, my class, and you can see that they cross over right at 60%, that's failing 60%. So everything to the right of here is passing, and certainly the alt room did better than the lecture room because the students were there. They weren't any better students. It was just random students. They showed up, which they don't do in the lecture class. They weren't Facebooking. They were doing things. So we think the success was they were involved. What a great way to teach. Get up out of your chairs, do something. They loved it. This chart is a little more interesting. We had 4 exams throughout the season, so we took the first exam as the base and then tracked the students' performance as they went along. Did they increase their performance or decrease their performance? Every dot's a student. 0 lines here, so anything below that line means that they decreased in performance throughout the year, and anything above it is passing or getting better throughout the year. 70% or 60% right here to the left is failing, to the right is passing. So this group of students are the ones in this big 200 class that improved and were passing the class. Not that many. That's the lecture class. This is the alt class. And we can see that chunk of students, where's 60, right here, is a bigger percentage of the class than the lecture. So students were improving as the semester went along in this classroom rather than fading away. What a neat class. How do we do that with our classes, guys? The room's sitting there waiting for us. Okay, so a lot of them. The other thing that we saw was the student, well, this class ended at 4:30. What time is it? 7. They wouldn't go home. 8 o'clock, I'm saying, I'm starving, you're out of here. And the students would come in hours beforehand and stay hours afterwards working on this stuff. Did they do that in your old classes? No. I mean, class is almost up, I'm out of here, right? They were really involved, so that was good. Then we decided to do labs in this room, and we had to come up with really neat labs, and the idea was that we would use cell phones as the detectors, not all that expensive lab equipment, but just these, and stuff we buy at Walmart. And we were going to do experiments like, how do you determine the density of the sun with a tree? How do you do that? I didn't invent this experiment. I wish I had. This is really cool. Okay. So the idea, this is the shadows on the ground, the light's coming through the trees, and you see all these different holes, but there's a minimum diameter. Nothing smaller than that, right? Why is that? Okay. So the light from the sun, an extended source, is going through a pinhole, the space between the leaves, and has a spot. So the spot may get dimmer, but doesn't get any smaller. So we can measure the diameter and kind of estimate some other things using Newton's gravitational equation and Kepler's third law, get all the way down in the volume of a sphere down to this one equation, which is the density of the sun using gravitational constant period of the Earth going around the sun, 365 days, and that angle. And you can tell the density of the sun using a tree. Now in the wintertime you have to use something else. Cool, huh? Man, I wish I'd invented that. So we came up with a lot of experiments based upon the cell phone, and this is data from an elevator ride. It's the accelerometer. Your cell phone has 3-dimensional axis accelerometer built into it. It has orientation sensors, magnetic sensors. It actually has a microphone. I don't know if you know this. It's just, your cell phone has a microphone in it. Camera, video camera, all these different sensors. And some proximity sensors, some are a little more touch sensitive than others, pressure sensitive. And so we would let the students measure the acceleration on an elevator ride and then go back and use this data to determine the height of the building. We got anywhere between 100 meters and a half a meter. Guys, it's 2 stories in a building. It's got to be, what, 6 meters, something? Something? So they didn't really think it through, but they got all sorts of neat answers. You'd put the cell phone in a baggie and put it on the edge of the table and let it swing back and forth. That's a pendulum, and it's amazing acceleration. Change the things of the pendulum, more weight in the baggie, longer strings, whatever. And they were doing this, and we wrote up a whole bunch of labs and put it in another book. The thing that really happened that was cool was students were saying things we never heard before. Oh, if I could do this, then I can do this at home. And they were thinking of experiments they could do with their cell phone at home. We don't get that in regular physics labs. So the fact that they owned the detector was probably the most important thing in these labs. And then they were on the floor. Okay. CDS, right. So now we're in the CDS department. Got this new class, Modeling and Simulation, which is for biology students. Remember the IB3 days, right? I came here to do bioinformatics, which we don't do anymore, the 10-month thing. Okay, well, now we're doing it in class. So things that we learned a long time ago, we're now using today. This is not atomic physics, by the way. This is where I started. It's not that anymore. Okay. The other thing we're working on, this is a class that's coming up, and we're writing another book on this. And the idea is that in the beginning of image processing, they had these papers which had these long descriptions, and the code was real long to do these things. Well, now we have Python and MATLAB with all these libraries, and we still have these long descriptions, and the code's only this big. Why are you giving me the description? I can read the code faster. It takes up less real estate. So something's got to change. We've got to come up with a new way. The other problem is everybody describes image processing differently. There's no standard to it. So we're going to make one. We're coming up with this operator notation that is as succinct as the coding is nowadays, and that the operators match up with functions that people call. So you can easily go from an operator notation to the calls in a Python script. You don't need several lines of code anymore. That's a window operator smoothing, change the color scheme of image A, correlate it with image B. That's like 5 lines of Python, because the module's already built. You just call them, right? I don't need 50 lines of equations. Do it in one. So the book is going to have all these different operators, and we'll apply them in that class. Due January 18th. We were just talking about that, right? Okay. So lots of image applications. This is one, a student graduated in the bioinformatics department. She was getting data from NOVA for patients that had idiopathic pulmonary fibrosis. Don't get this disease. 5 years after it starts, you're dead. And it takes 3 years to diagnose it. So the good news is you got 5 years left. The bad news is you've already used 3. But she was trying to identify the regions in a lung scan. This is a slice in a lung from a CAT scan that were diseased, and try to measure the area of the lung total to get the percentage of volume in the lung that was diseased, because the disease progresses at the bottom and then all of a sudden appears everywhere. And so they're trying to track when the prediction is. And at the time, there was no medicines, there was no cure, there was no help, nothing. That's getting a little better now. Other things we were doing were matching up, trying to build a connected graph of basic shapes that we find in images. Is there a basic set of shapes? All these images are from this set of shapes? If so, then we can diagnose the images. Had a student working on fly embryos. This is to the Howard Hughes data. That's a fly embryo. And all the proteins are on the outside. So it's not a volume, it's a flat thing, so we can lie it. So she was analyzing images like that. What are the proteins doing? Are these embryo over here like these embryo over here? That kind of thing. She graduated, got a job, went away. Okay. Lately is the GOAT project. This lady just graduated last year, and she worked for the USDA. And the idea was that in northern Africa, the farmers have goats, but nothing else. They don't have scales or access to any kind of way of measuring the goats. They're just on their own. They don't have formal education. They just what they learn from dad. But they do have smartphones. And so they can take pictures of the goats, send them off to our server, get them analyzed. And so she was developing the protocol for taking the pictures of the goats. Blue background, because no goat is blue. If the goat's blue, you already know it's sick. It turns out these things are shiny, but and that was kind of problematic because it's not a solid blue, and a cloth would work better, but these are goats, and goats do what goats do, and cloth doesn't work so well after an hour. But so she set up this protocol. We took a bunch of pictures, side pictures, front pictures, teeth pictures, eye pictures. We're looking at the conjunctiva, and then back pictures. We're not going to show you those. But she got written up. This is a federal document that talked about lots of different research, and she got put in that for a page, which was really cool. One thing I learned was that you must, this is true, you get lots of data, you have to handle it with care. Yes, you do. Because the data will rear its ugly head if you're not careful. That's the last time I'm handling a goat. This was in Virginia. I didn't go to Africa, but we had a color chart here to calibrate the images and stuff like that. And we could do texture on the goat coats. We could do the shape of the goats, relative shapes, how big's the barrel, how big is it to the withers, and the height and the number of hands, whatever she was doing. But that's the GOAT project. Okay? This is a little more biologically oriented. So in the cells, there are actin fibers. They're the structure of the cell. Everything based on these F-actin fibers. We can put dye on them and see them in a microscope. That's real stuff. But when you take the shape of the cell out of the body and put it on a slide, it changes shape, and that is messy. So this company in France developed these microstructures, which are these little patterns, and the cell will stick to that one pattern. So this cell is stuck to a pattern that is kind of this umbrella-looking, upside-down umbrella-looking thing. So all the cells have the same shape. Now we can compare one cell to the other and compare what's happening with these actin fibers to the cells that have disease or drugs to the ones that don't. Well, we wanted to know what are the energy terms in this thing. So we had 4 different energy terms, and then would simulate the movement of the actin fibers. And we had to have, they're on top and on bottom, so we had 2 different layers, and then they're different on the outside and the inside. So we had different types of fibers. And that was another student project. And so we wanted to get our simulation images to look like these images, and when we did that, we could say, okay, what was going on with the energy terms to make that work, and then go back to the biologist and say, we think this is what's going on. It's your job to handle it now. We're out of here. So we were at the bar at 4:30. The biologist didn't come until 7 o'clock. All right, so now we're moving on to the CS department. And the big problem people have is what's the difference between computer science and computational science? Computer science, of course, is the hardware stuff, right? The internet, how the internet works, compilers, operating systems. We don't care about that. The computers work fine. But both departments also have data and algorithms and stuff like that, right? So why are we different? What's in the question marks? Well, one thing is we're connecting with lots of different other fields. That's a nice picture. I'm not going to talk about it. Okay. It's kind of an interesting field. When I was over in the physics department, people say, who are you? You say, I'm a physicist. I'm an astrophysicist. But I'm a physicist. And everybody knows what that is. I am a physicist. What are you? Tell me.
Computational social science.
Computational social sciences? Usually what happens is people say, you blew it. They don't tell you what they are, but they tell you, I do this. I analyze this, okay? We don't have the titles yet. We don't have the street cred that mature departments have. And so that's just the thing. It was computer science was that way back in the old days, and now computational data science is that way. Okay, so the field is creating itself. In our department, of course, we have all these different things. I put image analysis on there because I'm the one talking, but we have these other things too. And then, of course, we're starting to connect with all the departments on campus that want to play with us. And not just College of Science things over in humanities and stuff like that, because everybody's got data. Everybody needs data. And so this is where computational data science is going to start deviating from computer science. We're going to learn lots of things. Okay? It's more than that, though. Yeah?
Can I suppose interject there, like, because there are other courses now which you can get like a master's in data analytics
Yep.
and this and that, and so it does seem like there's an arms race going back to those
Yes.
other
Yes.
fields that don't necessarily want to play with us. They'll just go and design their own.
So,
Their
I mean,
own
you talk to most of
code
a lot of departments here say, oh, we're big data. Yeah, right. Okay, so they may have data for their own specific thing, analysis for their own specific thing, but we're going to be a lot broader than that. Okay, our new data science center is not just physics or chemistry; it's everything. Lots of tools, lots of people.
Well, I suppose like going back, like there is a data analytics course.
Yeah.
Out of the engineering department, and they just market that straight to all the
Yep.
consultants, and they get a stream of.
Yep.
You go to one of those classes, and everyone works for Booz,
So we're competing.
Schneider, or something like that, and it's like.
Yeah, we're competing with
here's your
that.
career progression. You
Right.
go and do your masters at George Mason.
Yep.
and then-
So we're building that too.
Right.
Some of the pipelines we're working on aren't set yet, so I'm not going to say them, but we're trying to build the same kind of thing here. I've only been on the job 3 weeks anyway.
Come on, you got.
And the first week was hell. So. All right. Not only is the role of research changing, but the role of education is changing as well. You know who this is? This is Orsted. Okay. Right. Cool. No. All right. Physics people know who Orsted is. He taught back in the 1800s, and back then, we were on a stage, and you applauded us, and whatever we said, you said yes. Okay? And then so he was doing electricity and magnetism. Back then, they didn't think electricity and magnetism were connected. Electricity is over here, magnetism over here, they're not connected. I'm going to prove it to you. I have this wire. Now, this is 1800s. They didn't have a lot of good equipment. And I'm going to run electricity through this wire, and I'm going to put a magnet up to it, and the wire's not going to move. Therefore, they're not connected. Ha, ha. And the student said, sir, I saw it move. Back then, you didn't do that. So he said, oh. And so it's kind of like the father teaching. Okay? In the United States, we have the Orsted Medal to the top physics teacher every year named after this guy. That's Wallace Hilton. He won one. He was one of my things. And he was a very advocate of students getting involved even at a very early age. Don't just sit in the classroom, get involved. So he developed a whole bunch of physics experiments and stuff like that. Get involved, do it. It's the active learning from the 70s and the 60s and stuff. All right, in the old days, the universities and professors were what, the repository of information. Except for religious stuff, we had all the information. Okay? And if you wanted the information, you had to come to us. What a neat deal this was. Okay, so we were the dissemination of information. And we were also in charge of shaping lives. Back in the old days, you got connected. The old boys network, right? And that's how you did it. You went to university and got connected. So we shaped lives. Great, what a good job this is. Well, we quit that one a long time ago. We don't do that anymore. We got the internet, so we aren't the repository of information, and there's TED and YouTube, and so we aren't the sole disseminators of information. So what do we got left? Strike one, strike two, strike three. So the very role of education is changing, not only for the professors, but also for the students. What's your role as students? Are you here to gain knowledge out of a book? Or learn a new algorithm? Okay, logic. Every graduate course I've taught at George Mason, except for one physics course, I learned after graduation, not that graduation. All the graduation. None of that stuff that I teach was in my course. And no atomic physics either. Okay. Because the world's changing, and it's changing fast, and the technologies that we teach now weren't even available when I was in school back in the old days. Okay, so it's all changed. What do employers want? I've been asking around, and they want the ability to solve problems, not necessarily the ability to solve a particular problem. Given this, can you solve it? Can you manage projects? Can you bring people together? Can you work within our framework? Don't go rogue on us. Different technologies, not just data science or computational science or social science, but also health informatics and medical images and F-actin images and all these different things. You've got to learn other things besides the computer side of things. Of course, dirty data, we all know about that. They don't care if you solved a problem in class. That's rigged. They want to know, what are you really doing? Of course, can you do something nobody's ever done before? And this was a big one. Can you communicate? Can be idiot like me up here being silly. You remember things when I'm being silly, right? If I was up here being boring, you wouldn't remember anything. So you have to be able to communicate, both written and orally. Okay? What they didn't say was, oh, you need to know Python and Java and whatever. They didn't say, you need to know how to do graphs or image analysis. They know that you can learn all that stuff on the fly by Monday morning. Okay? And, you know, if you know 3 languages, the 4th one's easy, right? So that's not what they want. That's what they want. So where is the education in this? This is what you get in the classroom straight from the books, the online education, which we do, right? It's the interaction with the professors and the problems and stuff like that where this stuff comes into play. And that's where the real education is. What happens if you don't adapt? This happened to me. I got a phone call one day. This guy says, I'm a 10th grader, and I've been working with your algorithm. It's really cool, but I think we can do more with this. It's time to change fields when that happens. You have to adapt. You have to keep going. Don't get stuck in a rut. Okay? That's the same things. That just got repeated. The good news is, you're in the right field. These are starting salaries. That's 100K right there. Distribution, okay? What a neat deal.
That heavy deal?
What?
Sorry.
All right. Probably I shouldn't show this because all the students who are working on GRAs will get up and go get a real job. We had students, in the early days of bioinformatics, we had students do that. Bioinformatics was so hot, people were calling, I want to hire you now. I've only been in school for a month. I want to hire you now for $80,000. Okay, I'm out of here. 3 years later, the bottom falls out, and who's out of a job first? So get your education, then go get this stuff. Okay. So, the list goes on, right? Be adaptive, solve problems, make lots of connections. I know, it's not what you know, it's who you know. Yes. Okay? And understand that education is gathering of abilities, not book knowledge. You can do things. You've got confidence. I don't care what the problem is, I can do it. Okay? You have to understand that you may start off to be one thing, and then as life goes on, you're going to change into something else. Okay? And your career is going to go places you had no idea where it was going to go.
Is that you when you were younger?
No. I had a 10th grader do that. Okay, I do want to announce one thing. We have this DC data meeting. This is a meet and greet. This is not a conference. There's going to be one speaker talking on deep learning. It's snacks, drinks, and shake hands with people in the business and people in the DC community. It's free. It's on the Arlington campus. It's February 1st after hours. Sign up and go and shake hands. Tell people what a great place George Mason is. Okay, so I highly encourage that. We also send out announcements when we get job opportunities, internships. Every time I get something, it gets sent out. You've been getting those lately. But this is the hot one, and we're going to be there in force. I expect, hope you are too. Okay, that's it. Anything else? Now, as chairman, wait. As chairman, certainly if you have any issues, come on down, we'll discuss it, we'll figure out solutions, make it work. My office is, well, except when it's closed, it's open. And I'll be glad to talk to you about anything you want to talk about. Unless it's a social science problem, then I can't help you because I don't do this. Or finance, good God, no way. Okay. All right, any questions? No? Okay, exam. Yeah.
I'll get started.
Okay.
So with the new merging of the CSS program
Yeah.
into the myriad of other programs that were already in the CDS, from a student's perspective, it feels like there is a lot to be done in terms of merging. Still.
Like what?
Merging the student body.
Okay, I see what you're saying. So you're not talking about the education track, you're talking about...
No, I'm also talking about the education.
Okay, so
track.
you're on the same track you were when we started. If you're a CSS student, nothing's going to change on that.
Right.
We can't change once you've started.
No,
Okay?
but in general, in the future,
Yeah.
what,
Well, certainly we have to work on you're talking about the social thing, getting students to know each other and things
Sure.
like that. Yeah. We have to work on a pipeline to get students from the undergraduate to the graduate level. We need to get more graduate students involved in the undergraduate education. It's week 3, give me a chance. But that's a list of things to do. Of course, all that takes money and more students. The more students we have, the more opportunities we have to do that kind of thing. So go bring more students in. Okay? Talk to your local high school. Tell them what great thing, because nobody knows what's computational science. They all think it's computer science, right? So we're always looking for great eye candy. So if you have some great picture that you think would be great advertisement, we would love to use it. We want to get these 18-year-olds excited to come to George Mason or the Nova students. They don't want to see equations. They want to see how much can I make and is it really cool? I've got the chart for how much you can make. I need the really cool. Okay, what else we got? Yeah.
I'm not a student. I'm just here to learn if I
Okay.
maybe want to be a student.
Okay.
I don't have a data science background.
Okay.
And I feel really overwhelmed watching that.
Neither do I.
Okay.
I'm an atomic physicist.
Well, I don't have an atomic
Okay.
physics background either.
It was when computer science first started, the same thing. None of the professors had computer science degrees because they didn't have them, so everybody was from someplace else. What's your background? Physics? What are you? What's your background?
Economics.
Economics?
I'm a student. Computer science, I guess.
Okay, so he's physics again, optics, right? We're all from someplace else, and we learn as we go. Most of the introduction classes assume that you don't have the background. We're here to teach you these things. So don't be scared.
Okay.
Okay. You can certainly talk to any professor teaching class saying, these are my skills, is that okay? And they'll say, yeah, come on. This will be fun for me.